Yeah. So, we have seen that when the variable flow or sonic velocity or nozzle flow are there, right, and with the compressible gas flow. Now, I thought that why can't we use with some assumption, of course, and those assumptions are ought to be valid, and that why can't you use these relations for another engineering application, that is called pneumatic conveying. In many cases you have seen that, I do not know whether you have any industrial experience or have you seen any industry where conveying is being done. Normally that can be through bucket or through some chain and sprocket, things like that, in different mechanisms are there. But one such is also pneumatic conveying. Particularly I gave the example of spray drying. So, that spray drying, that dried material is also conveyed pneumatically, right. So, like that many things are conveyed pneumatically. The pneumatic conveying means with the help of the gas, that can be air, that can be any other, but generally air is free. We do not have to, till now we do not have to buy. I do not know in future whether you will have to buy or not, but till now it is not to be bought. But someday, now as it is, maybe couple of decades back, people never thought that somebody has to buy water, right. Now you have to buy drinking water everywhere, wherever you go, any part of the world you go, you have to buy the drinking water, and they are in the bottles, right. Couple of decades back, people did never think like that, that you have to buy. Now that is also in our country. You have to buy drinking water in many places, in many cities. Maybe you have to buy water itself, whole water you have to buy. So we don't know whether in future you have to buy air also or not, but as of now it is being free. So air is used as the conveying medium for conveying from one place to the other place. So if that be true, then can't we utilize till now whatever we have learned, whatever knowledge we have gained, with some assumptions that for this application, that pneumatic conveying, right. So if we look at, then let us see that in the Bernoulli's equation, which we started with, is it was like this. Okay, let me write that this is pneumatic conveying. So, for pneumatic conveying, so let me show you a figure. So, this is a typical pneumatic conveying, right. This is a typical pneumatic conveying. Things are conveyed pneumatically, and of course you have all other systems, but you are conveying through air pneumatically from one place to the other. So this is a typical example, right. So if we look at that Bernoulli's equation, so it was dP by rho plus V dV plus G dz, right, plus dF, this is equal to 0, right. We said that this is the pressure head, this is the velocity head, this is the gravitational head, this is the frictional head, right. If you want, we can also write that this is frictional head, this is gravitational head, this is velocity head, and this is pressure head. Right. So, all this put together, we got that Bernoulli's equation. Right. So, this we can rewrite that this to be also we have written earlier. This is equal to VdP because 1 by rho, V is equals to 1 by rho, right. So, VdP plus VdV plus GdZ plus dF, this is equals to 0, right. Now, let us assume that S be the kg of solid. Of course, in pneumatic conveying, it is solid which is conveyed, right. It is not normally any liquid which is conveyed pneumatically from one place to the other place. This is the solid which are being conveyed, mostly powders or very tiny small materials, they are conveyed pneumatically, right, whose density is also not so big. Then otherwise you have to use lot of force to convey from one place to the other place. For that let us assume S be the kg of solid, right, per kg of air conveyed, right, and Bs be the specific volume of the solid in meter cube solid per kg of solid, right. And now, here we are assuming since it is pneumatically being conveyed, that is from this place to this place it is pneumatically being conveyed, right. So, when it is being pneumatically conveyed along with the air, these solid particles are being conveyed along with the air. So, when it is happening like that, so can we assume that the energy equation which is being applied for the gas, this is for the gas which is being applied for the gas, can it be also applied for the solid? If we assume that, then we can say that S into Vs dP plus S VdV plus S GdZ plus d of Fs equals to 0, right. So, if it is for the gas, this is for the solid, right. So, dFs, this includes all frictional energy and any other energy losses, right, to the solid. So, if we assume that, then by adding these two, we can write V plus SVS into dP, right, plus 1 plus S into VdV, right, plus 1 plus S into GdZ plus dF plus dFs, this is equals to 0, right. Now, generally V is equals to say 0.8, whereas Vs equals to 0.0016. So, by and large, so wide. So specific volume of the fluid is much higher than that of the specific volume of the solid, because density of the fluid is much lower than that of the solid. So, specific volume of the gas or fluid is much higher than that of the solid. So, we can write that S times Vs is, this is much smaller than that of the V, right. If that be true, then we can neglect this term, that SVS term. So, we can write in that case, also one more thing we could assume here, that this dF and dFs, this put together is some say alpha dF. Alpha is not known, alpha is a constant. So, this dF and dFs, these two together, if we assume to be alpha dF, then we can rewrite that equation, that V dP, because we have neglected SBS much smaller being that of V, right. So, V dP plus 1 plus S into V dV, right, plus 1 plus S into G dZ plus alpha dF, this is equal to 0, right. If that be true, then we can write that, say this equation, earlier of course we have not given name of the equations. So, if this is gas, say for 1, this was for solid, where it was for solid, say this is for 2, and it is for combination, say for 3, right. Now, we know that G is equals to rho into V, that is the mass velocity, right. This is called mass velocity. If G is rho into V, that is mass velocity, then we can write that V is equals to G by rho, right. Then we can write V is equals to G by rho is equals to G into V, right. Oh, this is small, okay. So, G is equals to rho into V, that is mass velocity, right. So, it is V is equals to G by rho, GV, right. Or we can also write dV, this is equals to G dV, right. Or we can also write V dV is equals to G square V dV, because this dV we have already seen is G dV, right, and V we have seen is GV, right. So, G and G square, and this V is coming, this V is coming, and dV, right. So, dV dV is G square V dV, right. Therefore, we can write PV is equals to RT by M, not there, therefore, okay, we know that PV is equals to RT by M, therefore, V is equals to RT by M into P, right. Therefore, here we can write that dV over dP, this is equals to minus RT over MP square, or dV is equals to minus RT over MP square dP, right. So, dV is minus RT by MP square dP, right. Therefore, we can write V dV is equals to minus RT square over M square P cube dP. This is by substituting the value of V is RT by MP, right. So, if we substitute V dV, dV value is this with V times, so RT by MP square. So, this becomes square and this was square already. So, it is cube dP, right. So, if we say this, then we can substitute these and rewrite the equation this number 3 as integrating and rewriting, that we can write RT by M, right, between 1 to 2 dP over rho, right, plus 1 plus S. This we can write GRT square divided by M square, again 1 to 2 dP over P cube plus 1 plus S times G between 1 to 2 dZ, plus, if we write that dF is in terms of frictional loss, if we write that, then we can write 4 alpha F L by D, right, between 1 to 2, again V d V is equals to 0, right. So, this on simplification we can write that RT by M ln of P2 by P1, RT by M ln of P2 by P1, right, minus 1 plus S into GRT square divided by 2M square times, since it is P1 to 2, so 1 by P1 square minus 1 by P2 square, right. This plus 1 plus S times G into Z2 minus Z1 minus 4 alpha F L by D, this 4 alpha F L by D G R T square by 2M square. This is again we can rewrite that V dV earlier in place of dP. So, that can be 1 by P1 square minus 1 by P2 square, right. This is equals to 0. So, we can rewrite that minus RT by M ln of P1 by P2, right, minus 1 plus S GRT 1 plus S GRT square by 2M square times 1 by P1 square minus 1 by P2 square. If we write minus 1 plus S into G into Z1 minus Z2, right, minus 4 alpha F L by D G R T square by 2 m square, this times 1 by P1 square minus 1 by P2 square. This is equals to 0, right. So, we can write by taking all negatives RT by M ln P1 by P2 plus, if we take this thing common, 1 plus S, 1 plus S was already there. So, 1 plus S G into Z1 minus Z2, right, plus, if we take common, then 1 plus S plus 4 alpha F L by D times G R T square by 2 m square into 1 by P1 square minus 1 by P2 square. This is equal to 0, right. So, from here, if we know many things, we can do the calculations for the either velocity or the pressure as and when it is required, right. As and when it is required, we can do. You see, RT by M, R is known, the temperature at which you are conveying is known, molecular weight of the fluid, if it is air, is known. Either of the pressures you know, either P1 or P2, right, either inlet pressure or outlet pressure you know, that is assumed that you should know, right. So, everything cannot be from one equation, or you can only solve one unknown, there is no ambiguity in that, right. So, here some of the things normally as an engineer you would like to know that you want to send this much material, maybe powder or some granular material. So, this much material you want to send from one place to the other. So, what should be the pressure drop? That is one fundamental thing which you want to know, because that will dictate major investment from your side, right, in terms of pumps and others, motors, all these will be dictated by that. So, there you would like to know if the inlet pressure is so much, what is the exit pressure, or the vice versa. If the outlet pressure is so much, then what was the original inlet pressure. So, if this is known, then only you can say, yes, I have come to know, and we can find out, right. So, here this is known, S, the quantity of the material being conveyed is known, G from that place is known, how much distance you are covering, that is known, right. So, here one thing which can be generally unknown is that alpha, right. Alpha we had taken that df plus dfs, if you remember, we had taken that df plus dfs to be alpha df, right, and then subsequently that df we had substituted with the frictional loss, right, that from the earlier equations where we found out the fanning friction factor, right. So, that we are taking here also, that is the frictional loss. So, if we had taken that, so this alpha can be either known or unknown, right. The moment this alpha is not known or unknown, then you can play with that. If you know the pressure drops in the two places, like as we had shown earlier. So, okay, if you know that pressure drop in the two places, from here you are conveying to that place. So, this place pressures you know P1 and P2. Then for a known system you can find out the alpha value, right. For that, the length, diameter, this is the diameter, length, how much length it has covered, like this, then from there like this. So, how much length it has covered. So, that if it is known, how much Z, if there be at all. So, this is the Z, if there Z is conveyed, how much that is known. So, if these parameters are known, your G mass velocity is known, R is known, temperature is known. So, you can and M that is the molecular rate of the conveying medium, right. Generally it is air, right. If that is known, then you can play with that. Okay, I know the pressure at the inlet and outlet. Let me find out the coefficient alpha. The once alpha of that system is known, then subsequently for a different unknown pressure combination, you can find out either P1 or you can find out P2, right. So, given P1 or P2, alpha you have already determined for that system, and from there, by knowing all other parameters like length, like height, like distance, like diameter of the material, if all these things are known, then you can also determine the pressure. Because as I said, this kind of process where you are pneumatically conveying from one place to other place, it is how much energy is required, that is your fundamental thing. Whether that is too much in terms of energy requirement, and you need to support with lot of maybe pumps, motors and all accessories. So, whether that investment will be suitable or not, to judge with that, how much pressure will be fallen or drop will be there, if that is to be known, then this I thought that this can be a preliminary idea about the pneumatic conveying system, right. Again I am saying that I have thought of this, that if the fundamental assumption which we made here is that we want to convey the solid through the fluid. Now, if the fluid can have the equation, can we assume the same fluid which is also carrying with this material, can that material also be brought into this? Obviously, some assumptions also we made, not assumptions, that is the reality, that the specific volume of the solid is much less than that of the fluid, or in this case air. So, if that be true, then specific volume we separated, and we said that this much kg of solid is conveyed per kg of the fluid or say air. So, that is of course has to be known, right. So, if this way, if we can find out the pressure drop or the coefficient of this friction or whatever you call alpha, that if we can determine, then I hope we can guess, we can have some idea about the drop in pressure. Okay. So next time we'll try to really calculate or see the numerals, how they are coming up. Okay. Thank you.